This Cartesian plane plots the linear function f of x equals x plus 5, with a specific highlighted coordinate right at the point 2, 7. Evaluating the exact value of this function at an x-coordinate of 2 is straightforward algebra. You input the 2, and the system outputs a 7. But if we remove that specific data point, we create a void in the geometric structure. This leaves us with a structural problem. Without an exact defined value at x equals 2, we need a method to mathematically determine how the function behaves immediately surrounding that empty coordinate. Finding a static coordinate is basic arithmetic. Plotting the trajectory approaching a missing coordinate requires a completely different analytical tool. That tool is the mathematical limit. Limits allow us to evaluate these approach trajectories rather than static points. By analyzing how a function behaves as it gets closer and closer to a target, limits provide the foundation for proving structural continuity in any mathematical system. Proving that continuity requires a function to pass a strict three-part algebraic test. To build those three rules, we first have to step back and analyze the raw, discrete data of an approaching line. Mathematical continuity is not defined by visually drawing a line without lifting your pen. It is determined by a rigorous algebraic proof governing converging values. This dual-pane diagram maps our function f of x equals x plus 5 on the left alongside a raw data table on the right. We will track the output as the input value creeps toward 2 from the negative side. When we input an x value of 1.9, the function evaluates to 6.9. Stepping closer to the void, an input of 1.99 yields 6.99. Closing the gap further, 1.999 yields 6.999. And moving micro-marginally close, 1.9999 evaluates to 6.9999. The data reveals a clear pattern. As the input incrementally steps toward 2, the output systematically trends toward exactly 7. This specific converging trend is defined as the left-hand limit. The formal mathematical notation represents this with a negative superscript next to the approach value. It dictates that as x approaches 2 from the negative direction, the destination is 7. A left-hand limit calculates a definitive numerical destination based solely on data from one side. To verify that destination, we evaluate the approach from values greater than 2 on the positive side. Starting our descent, an input of 2.1 yields an output of 7.1. Stepping closer from above, 2.01 yields 7.01. At an infinitesimally close input of 2.001, we get 7.001. This descending numerical approach converges precisely on the same output of 7. This incoming value from the positive direction is the right-hand limit. This creates the primary rule for a limit's existence. The destination predicted from the left must perfectly match the destination predicted from the right. A general limit only exists at a coordinate if both independent directional trajectories agree on the exact same finite numerical value. Predicting a destination is different from actually arriving there. A limit only tells us where the function is heading, not what happens when it lands. To prove the function remains structurally unbroken upon arrival, it must pass the three continuity conditions. Condition 1. The function's actual value at the target coordinate must be a finite number. Condition 2. The general bilateral limit of the function as it approaches that coordinate must exist. Condition 3. That general limit must perfectly equal the function's actual defined value. Passing this exact three-part alignment test is the singular way a mathematical function is proven to be unbroken at a specific point. This graph visualizes the rational function f of x equals 1 over the quantity x minus 5. We will test its continuity specifically at the coordinate x equals 5. Running condition 1 requires us to evaluate the function exactly at the target coordinate. Substituting the input leaves us with a calculation of 1 divided by 0. Division by 0 yields an infinite state, which means our result is not a finite number. Because the outcome is not finite, condition 1 fails instantly. When algebraic conditions result in an undefined or infinite state, the geometric structure fractures, making mathematical continuity impossible. These three continuity rules also give us a framework to reverse engineer and repair undefined systems. This piecewise function brackets a system where an unknown constant m dictates the exact value at x equals 5. For all inputs everywhere else along the line, the system is governed by a standard algebraic curve, leaving a gap where m currently floats randomly above. Our objective is to calculate the precise value of m that will force the entire piecewise system to be mathematically continuous. The path to solving this lies strictly in Condition 3 of our continuity checklist. Condition 3 states that the function's target limit must equal its defined functional value. To calculate that missing value, we first ignore m completely and solve for the bilateral limit of the surrounding curve as it approaches the coordinate of 5. Setting up the limit calculation for the surrounding curve as x approaches 5, we process the step-by-step simplification. The complex algebraic limit evaluates cleanly to the number 5. The trajectories from both directions aim precisely at this coordinate. Following the rules of the continuity axiom, we align our known values into a final equation. For the third condition to hold true, the constant m must be exactly 5. Calculating the limits from both independent directions precisely provided the exact coordinates needed to bridge the undefined gap. The structural integrity of a point in mathematics relies entirely on passing these specific conditions. Measured, final tone, continuity is never a visual assumption. It is an absolute algebraic guarantee, forged by bilateral limits and strictly defined outcomes.